The following program is brought to you by Caltech.
Welcome back. Last time we introduced support vector machines. And if you think of linear models as economy cars, which is what we said when we introduced them, you can think of support vector machines as the luxury line of those cars. And indeed, they are nothing but a linear model in the simplest form, except that they actually are a little bit more keen on the performance. And the key to the performance was the idea of the margin, is that if the data is linearly separable, there is more than one line that can separate the data. And if you take the line that has the biggest margin, furthest away from the closest point, then you have an advantage. It's both an intuitive advantage and an advantage that can be theoretically established, which we did through the idea of the growth function in this case. And after we determined that it's a good idea to maximize the margin, we set out to do that. And after a chain of mathematics, we ended up with a Lagrangian that we are going to maximize. And the Lagrangian has very interesting properties. It's quadratic, so it's a simple function. And the constraints are inequality constraints, very simple inequality constraints in this case, and one equality constraint. And we are not going to actually do the solving ourselves. We are going to pass the problem on to a package of quadratic programming. And then we will wait for quadratic programming to give us back the values of alphas. Now, quadratic programming will have problems with solving this if the number of examples is bigger. Okay, so once you get to thousands, it becomes an issue. And then there are all kinds of heuristics to deal with that case. And in general, quadratic programming sometimes needs babysitting, tweaking, limiting range, and whatnot. But at least someone else wrote it, and we only have to do these things in order to get the solution rather than to write this from scratch. So it's not a bad deal for us. And once we get the alphas back, there is a very interesting interpretation that happens. You look at the alphas, the Lagrange multipliers, and some of them will be greater than 0, and most of them will be 0. Should be identically 0. In reality, because of the rounding error, you might get them very, very small, and you set them manually to 0. But the guys that happen to be bigger than 0 are special, and they are called the support vectors. And whether you are working in the X space or took the X space and moved to a Z space and moved back here, the support vectors are the ones that achieve the margin. They are sitting exactly at the critical point here. And they are used to define the plane. And the most important aspect about them is the fact that you can predict a bound on the out-of-sample error based on the number of support vectors you get. And it is the normal form of dividing the complexity in terms of the number of parameters, in this case, the non-zero alphas, or the number of support vectors that corresponds to it, divided by more or less the number of examples. We have seen that before. But the key issue here is something really worth noting. The right-hand side, without the expected value just tell us that we have to average this over a number of cases for this to be true. We are dividing the number of support vectors by n. Okay? The number of support vectors is an in-sample quantity. You do all of this, you get the alphas back, and you can tell what the number of support vectors are in sample. Okay? So we are able to check on the out-of-sample error using an in-sample quantity. And we know by the previous experience that this is a biggie. Okay? Because now not only are we going to check on the in-sample error, we are also going to check on the out-of-sample error using a quantity we can measure. Okay. Now, we applied support vectors only to linearly separable data, at least in the previous lecture. In this lecture, we will generalize that. And in order to deal with cases where the data is not linearly separable in the X space, what we did is we used nonlinear transform, as we did before with linear models. And a curious thing happened when we did that. Because we went to a fairly high dimensional Z space, and we got a surface that is, wiggly and so on, which in our mind raises alarm bells as far as generalization is concerned. But we ended up with something that can be stated in a simplistic form as we get a complex hypothesis, which is the snake. Okay? But we don't pay the price for it in terms of the complexity of the hypothesis set. Remember, the complexity of the hypothesis set is what we pay the price for in terms of the VC analysis, right? And it is typically the case that when the capital H is more complex, or script H is more complex, each individual is also complex. But here we sort of did some cheating, and we managed to use a high-dimensional Z-space. Okay, so it's a complex script H, complex hypothesis set. But the hypothesis we get is really, although it looks very, very complex, it really belongs to a simple set because it maximizes the margin. So we get the benefit of a fairly low out-of-sample error, in spite of the fact that we capture the fitting very well by getting the 0 in sample error. Now, this is exaggerated, I grant you that, but it has an element of truth in it. And it captures what support vector machines do. They allow you to go very sophisticated without fully paying the price for it. Okay, so today we are going to continue this by extending the support vector machines in the basic case. And we are going to cover the main method, which is the kernel methods, in the bulk of the lecture. And the two topics are the kernels, and referred to as the kernel trick actually formally. And that takes care of the nonlinear transformation when the Z-space can be very sophisticated, so sophisticated that you can't even write it down. It's an infinite dimensional space, okay? Which would be completely unheard of if you're using plain vanilla linear models. The other topic is to extend support vector machines from the linearly separable case to the non-linearly separable case, allowing yourself to make errors, okay? So this is pretty much that if you were using perceptrons and went to pocket, this would be if you went from the support vector machines that we introduced, that we are going to label now hard margin, because they strictly obey the margin, to a soft margin that allows some errors, okay? And both of these extensions will expand your horizons in terms of the problems you are able to deal with, and the chances are in a practical problem, you are going to use both. You are going to go to a high-dimensional space, sometimes an infinite dimensional space without paying the price for it, as we will see in a moment. And in addition to that, you are going to allow some errors in order not to make outliers dictate an unduly complex nonlinear transformation. So both of them will come in handy. Okay, let's start with the kernels. So the idea of the kernels is that I want to go to the Z-space without paying the price for it. And we are already halfway there. If you remember from last lecture, the way Z manifests itself in the computation is very simple, okay? You do an inner product in the Z-space, and from then on, it's a regular quadratic programming problem, and the dimensionality of the problem depends on the number of examples, not on the dimensionality of the Z-space, once you get the inner product. And when you get the result back, you count the number of support vectors, which really depends, again, on the number of examples, not the dimensionality, okay? Obviously, the dimensionality will come in because you may end up with such a wiggly surface that every other vector becomes a support vector in order to support this type of boundary. But basically, the dimensionality of Z explicitly doesn't appear. Nonetheless, we still have to take an inner product in the Z space, okay? So in this view graph, I am going to zoom in to the very simple question. What do I need from the Z space in order to be able to carry out the machinery that I have seen so far? Okay? So what do? We have a Lagrangian to solve. Okay, so the Lagrangian looks like this. And since we are interested in what we do in the Z space, I'm going to make these purple. Okay? So in order to be able to carry out the Lagrangian, I need to get the inner product in the Z space, okay? But getting an inner product in the Z space is less demand than getting the actual vector in the Z space, okay? Think of it this way. I am a guardian of the Z space. I'm closing the door. Nobody has access to the Z space, okay? You come to me with requests, okay? If you give me an X and ask me what is the transformation, that's a big demand. I have to hand you a big Z, right? Okay? And I may not allow that. But let's say that all I am willing to give you are inner products. You give me X and X dash. I close the door, do my thing, and come back with a number, which is the inner product between Z and Z dash, without actually telling you what Z and Z dash were. Okay? That would be a simple operation. And if you can get away with it, then that's a pretty good thing, because now we can completely focus on inner products in the Z space and see if that can lead to a simplification. So in this slide, we are going through step by step in the entire process to see if we ever need anything out of the Z space other than the inner product. Okay, so in forming the Lagrangian, we need the inner product, okay? Let's look at the constraints. We have to pass the constraints to quadratic programming. Okay, so this is the first constraint. I don't see any Z, so we are cool. The other one, the equality, I don't see any Z either. So if you have an inner product in the Z space, you are ready with the problem that you are going to pass on to the quadratic programming. You gave it to quadratic programming, back comes the vector alpha, alpha 1, alpha 2, up to alpha n. Now you need to implement your function. You are not just solving this. You actually are going to hand a hypothesis to your customer, right? And the hypothesis looks like this. Now I look at this, and now I'm a little bit worried because here is W and Z, although this is an inner product. It's not an inner product between points in X, between W, and I don't know what W is. W lives in the Z space. So I want to make sure, can I get away with just inner products in order to solve this? Well, W is no mystery to us. We have solved for it explicitly. And we found that you can find W by adding up over all the vectors, but in particular over the support vectors that happen to have non-zero alpha, this quantity. If you take this quantity back and plug it in for W, what do you get in terms of what you need to compute? You need to compute inner products. Okay, that's encouraging. Okay, one more item. This innocent-looking B is loaded. Okay, this is one of the parameters that we solve for. Okay, maybe that's what will kill us. Let's see. How do I solve for B? I solve for B by taking any support vector and solving for this equation. So I take a support vector M, okay, and plug it in. Okay, am I in trouble because I have the W? No, we already saw that W is here. It has this form, so I can plug it in here, and all I need in order to solve for B here is this fellow. Done. We only deal with Z as far as the inner product is concerned. Now that raises a very interesting possibility. If I am able to compute the inner product in the Z space without visiting the Z space, I still can carry this machinery. Okay? We can even move further. Okay? If I can carry the inner product in the Z space without knowing what the Z space is, I still will be okay. Okay? You may wonder, how am I going to do that? That's a different question. Okay? But all we need to do now is something. I give you X and X dash, 2 points in the X space. You do your thing, come back with a number, and promise me that this is the inner product in the Z space, the mysterious Z space. And then I will do all the support vector machinery in your space that I never visited, and come up with the support vectors which live in your space, and get the performance based on the number of support vectors, and deliver to the customer and tell them I used really a very sophisticated space. And then they will ask, what is it? And we usually, we have our stunned silence moments in machine learning where you do something and you know that the existence is sufficient. Okay. So let's look at this idea as being a generalized inner product. X and X dash, we transform them and take an inner product in the Z space. We are going to treat it as if it was a generalized inner product in the X space. So what are the components? You take 2 points. We are going to label them X and X dash in the input space. And we need this quantity. Okay? So this quantity is a function of X and X dash. That much we know. We don't know which function, but it's a function. Why is that? Because Z is exclusively a function of X. Z dash is exclusively a function of X dash, being transformed versions of them. And therefore, their inner product will be a function that is determined by X and X dash. Okay? So this is the function that I'm looking for. Okay. Now we are going to call this the kernel, hence the name. Okay? So this is the kernel we are going to use. A kernel will correspond to some Z space. Okay? And as I mentioned, this will be labeled as an inner product. I put it between quotation because it's general, between X and X dash. It's not a straight inner product, but an inner product after a transformation. Okay. Now let me give you an example, okay? It's a bit of a simplistic example, but just to illustrate the idea. Let's say that I have X being two-dimensional Euclidean space. So I have 2 coordinates, x1 and x2. And I'm using a nonlinear transformation, which happens to be second-order polynomial. We have seen that a number of times, okay? So what do we have? We have a transformation that takes the vector x, produces the vector z, and that would be the full second-order guy. So we have 6 coordinates corresponding to all terms of the second order involving x1 and x2, and this is the guy. We used that before, okay? And therefore, if you want to get the kernel, which is formally the inner product between the transformation of x and x dash, you will get this. Nothing mysterious. You're just going to substitute for this for x and substitute for it again for x dash, multiply the corresponding terms and add them up, and this is what you get, okay? So the only lesson we are learning here is that indeed this is just a function of x and x dash, okay? If I didn't know this was an inner product, I can look at this. Okay, this is a function I can compute, okay? Fine. Now we come to the trick, okay? Can we compute this kernel without transforming x and x dash? Okay? So let's look at the example again, okay? I'm going to now improvise a kernel, okay? It doesn't transform things to the Z space and then does the inner product. It just tells you what the kernel is. And then I'm going to convince you that this kernel actually corresponds to a transformation to some Z space and taking an inner product there, okay? So here is my kernel. It's function of x and x dash, and it happens to have that form, okay? This is a special form that will help me later on. But the main thing you would want to look at it is that this is not an inner product in the x space, in spite of the fact that it involves 1 computationally. I take this, add 1, and square, so this is just a function. I happen to formalize it in terms of an inner product just because it's simple. So this is a function, okay? This is also not clearly an inner product in any other space, transformed or otherwise, okay? It is just a function, okay? So now I'm going to take this function, and I'm going to write it explicitly in terms of the components. I'm still working with 2-dimensional input. So this would be, you know, the inner product here would be x1, x1 dash plus x2, x2 dash. So this is the quantity that I have. And I can definitely square things, and I get this quantity. Okay? So this is the value of the kernel. Now, this looks awfully familiar, okay? It looks like an inner product except for these annoying 2's, okay? This would have been as if I transformed to the second order and took it, except that have these guys, okay? But is this going to discourage me? No. This still is an inner product, and the transformation to the space that makes this an inner product is this fellow. X goes to this. See, I put a square root, okay? Nonlinear transform, I can put anything, right? This is my transformation. The only test you need to ask me is whether I applied exactly the same transformation to x dash. Yes, I did. So that is indeed a transformation of x into a z. And when I take the inner product, what do I get? I get my kernel. Okay, good establishment of concept here. But the idea is this, okay, that's a lot of fuss about nothing, really. I could have done this in the first place. Now, think of what happens if I am, instead of taking 1 plus x to the 2, I do it to the 100. Look at the difference between computing this quantity and actually going to the 100 order transformation. Getting is expanded and getting the other one expanded and then doing the inner product. So let's see how this works. That's called the polynomial kernel. Okay? So now I take a d-dimensional space, not 2, but general D. And I would like to take a transformation of that space into qth order polynomial. Okay? And here is my kernel, the equivalent kernel. I'm putting it between quotation because the square root will happen here again in abundance. Okay? But it's just a scale. Okay? The main idea is still there. So here is my kernel. I get 1 plus x that to the q. Okay? First, establishing what does it take to compute this. Okay? I don't know yet whether this is a kernel, a valid kernel. A valid kernel is an inner product in some space. I haven't seen that yet. I pretty much suspect that it will be by the previous argument. But it will become clearer when I do this. Okay? So when I evaluate this, okay, so this is the inner product. Now I have d dimensions. So I have d of these guys corresponding to each other, and then multiply them raised to the power q. How much computation does it take you to do this? Okay, I have d multiplications here. That's the dimensionality of the x space. And then I need to raise it to the power q. Whether q is 10 or 100 or a million, it's the same complexity. What I'm going to do, I'm going to take the logarithm, multiply it by q, and exponentiate. It doesn't matter what this fellow is, right? This is a number. I'm not expanding them. I'm just plugging in these, and this becomes a number, raising it to the power 100 or raising it to the power 1,000, okay? So this is a very simple operation to carry out. Now, think of what happens if you were actually taking d equals 10 and q equals 100. And you can see that if I actually expanded this conceptually, not computationally, it's very convenient because every time an x appears, the x dash version of it appears. When I multiply any combination, that will always be the case. I will get a tremendous number of terms, which are all orders up to q of different combinations of the x's. And I will have a huge expansion here. And it shouldn't be a surprise that I will be able to decompose this into something of x dot something of x dash, because every term here appears with both x and x dash. The same trick we did here, except more elaborately. But if you actually go at it explicitly, you have to give me the entire vector in the z space that results from a 100-order polynomial transformation of a 10th order guy. This will be an ugly beast to deal with, okay? And now I can do this just computing this number, just a number. Take your x and x, get this number, raise it to the power q, and I already have, as if I visited the z space and got that number there, okay? Okay, so if you're worried about the square root of n, because obviously, you know, we will get this, but you will get a bunch of combinations. This gets here, and now you are power 100, so there will be all kinds of combinations. So you will get a bunch of constants in front of the terms, and you are going to square root them in order to get it to be a canonical transformation. You can adjust the scales a little bit, not fully, by taking your kernel instead of being 1 plus. You have scales a and b that will mitigate a little bit the diversity of the coefficients you get here. But the bottom line is that a kernel of this form does correspond to an inner product in a higher space. And by computing it just in the x space using this formula, I am doing all I need to do in order to carry out the SV machinery. Okay. Now, with this in mind, so I did this by construction because it's easy, polynomial, and we can visualize it. We can get it in the 2 case and extrapolate mentally for the other case. Now, we realize in this case that we only need z to exist. In this case, I showed you what z is explicitly in the case of d equals 2 and by sort of hand waving in the case of the bigger case, but you can visualize what z is, okay? So now, let's get carried away and try to just get a kernel that maps us to z without even imagining what z is. So this is the case. Okay. So we take this to be an inner product in some space z. And once you do that, we are good with the entire machinery and the guarantees, and we will get the support vectors, and we will get generalization bound, all of the above. Okay? And here is an example of a kernel. Okay? This would be a useful kernel. Okay. Let's look at it. Okay? It's definitely a function of x and x dash. That's as much as I would require, the minimum requirement for this to be true, okay? And now, it doesn't even have an inner product term clearly, okay? Either in x space or z space, and I have no idea what that is. I can compute it. And my question is, does this actually correspond to some z space, an inner product in z space? So is this equivalent to taking each of them by itself, transforming it into a z in that space, and taking a straight inner product between z and z dash? Do I get the same number by visiting some space? Okay? So the answer is yes, and the interesting thing is that that space is infinite dimensional. Okay? So by doing this operation, which is not very difficult to compute, you have done an inner product in an infinite dimensional space. Congratulations. Okay? And you will get the full benefit of a horrific nonlinear transformation. Okay? And you don't worry about the ramifications of the going to an infinite dimensional space. So if I in the 3rd lecture when I introduced linear models, I told you go to an infinite dimensional space, you would probably be screaming at me because the generalization issues become completely ridiculous. Okay, but here we don't worry. We'll carry the machinery, and then we'll count the number of support vectors. If I have 1,000 examples and you only have 10 support vectors, I know I'm in good shape. Well, if I get 500 support vectors, tough luck. Okay, it was a nice try. Okay, so there is no harm done. Okay, So let's look at the infinite dimensional space. So I'm trying to convince you that this indeed is the case. So what I'm going to do, I'm going to take a simple case that I can illustrate. Okay? So let's take the kernel, but apply it in this case to one-dimensional space. So x and x dash are both scalars. So I call them x and x dash. And I'm going to take gamma to be 1, which is my modulating constant here. So I get this fellow. Okay? So now let me express this using Taylor series. First, I do the following. I expand this, so I get x squared, x dash squared, and minus twice x dash, and minus twice gets the minus and becomes a plus. Okay? So I get e to the minus x squared, e to the minus x dash squared, e to the 2x x dash. Okay? So that's the legitimate expansion of this. Okay? So now I take this and expand it using Taylor, and I get this fellow. This is, you take whatever the argument is, raise it to the power k, divided by k factorial, sum up from k equals 0 to infinity. That's the Taylor series for the e, right? Now I conveniently took out the x dash to the k, x to the k, and 2 to the k separately. This is just to put it in that form, and I get that. Okay, that's very nice. You seem to be complicating matters rather than simplifying it. Okay. Remember, my purpose is to convince you that there is a z space in which this is an inner product. So now look at this last line, and miraculously, some terms will turn blue. Keep your eyes on it. Oh, you see where I'm going with this. The guys that go with x have turned blue. The guys that will go with x dash have turned red. Okay? And why am I doing that? Because I am going to separate this into an inner product, something coming from x and something coming from x dash. And I want to make sure that it's the same. Once it is the same, then the dimensionality is really this summation. Each of these is a coordinate, and this is the contribution of the inner product to the inner product by this coordinate. So here I am getting this x dash multiplied by x. Both of them normalized by e to the minus x dash, etc. So if I want to see what is the transformation of the first guy, it would be e to the minus x squared multiplied by x to the k. That's one coordinate. And as k goes from 0 to infinity, I get different coordinates. I would be ready to go except for the annoying constants. So let's put them in purple. Okay? What do you do with them? You divide them between red and blue. Take the square root of that and put it in the red, and take the other square root and put it in the blue. And now we have formally two identical vectors. One is the transformed version of x and one of the transformed version of x dash. And this is the inner product, and it happens to be an infinite dimensional space because you are summing for 0 until infinity. Okay? So now this is a very interesting kernel. It will actually be it's called radial basis function kernel. If that rings a bell, indeed that's the subject of the next lecture. Okay? So let us look at this kernel in action. And it's very interesting because it's a very sophisticated kernel. It corresponds to an infinite dimensional space. Nonetheless, we can carry it out by computing a very simple exponential between the x points. So let's look at it in action. Okay. I'm going to take a slightly non-separable case in the x space. I mean, after all, I'm taking this glorious nonlinear transformation. I'd better have something which is not linearly separable in order to show you the goods. Okay? But I'm taking it slightly in order to make a point. Okay, so this is my target function. Okay? So if I generate points from here, the chances are it will not be linearly separable because just this wiggling will result in that. And indeed, I'm going to generate 100 points at random, and I get them here. And if you look at the 100 points, there is no line to separate them. Okay? Okay, so now what I'm going to do, I'm going to lighten the target function because the target function did its job, generated the examples, but I'm going to leave it in order to compare it with the final surface that we get. So I'm just going to have it as a light surface. You can't even see it probably. It's a now green surface, okay? So this is the data set that I'm working with. Okay, so this is a slightly non-separable case. And now I am going to transform x into an infinite dimensional space, okay? Someone else worries about that. All I'm doing in my mind, I am effectively doing that by just computing the kernel instead of just the simple inner product in the x space, okay? And the kernel is the kernel I got from the last slide, which happens to be a simple exponential. I compute it and get that, okay? So what happens when you do that, okay? So you get the kernel, you pass it on to quadratic programming, and quadratic programming gives you back the support vectors, okay? okay? So you get the support vectors. Let me magnify it. Okay. So you have the two classes, and I darkened the points that ended up being support vectors, okay? So these 1, 2, 3, 4 blue guys, and in the red, I have 1, 2, 3, 4, 5. I have 9 support vectors altogether, okay? Okay. Now, it's very interesting. 9 support vectors, how many points? 100 points. Can you tell me what is the out-of-sample error? Can you bound it above? Oh, it looks like it should be less than 10%, okay? I have gone to an infinite dimensional space. You are a witness to that, right? Okay? I used what is effectively an infinite number of parameters, okay? Completely suicidal in terms of generalization, okay? But hey, I get 9 support vectors, I can claim victory, okay? So now let's look at the surface in the Z space when I transform it back here, okay? So again, the Z space is a mysterious guy, okay? It's a, it's a hyperplane of degree infinity minus 1, okay? That's very nice, okay? And now I am trying to transform this to this space and look at it, and it looks like this. Okay? How did I get that? I didn't go to the Z space. What I did, I classified every point on the grill and said, and so when it transforms from -1 to +1, that's my only tool, okay? But I can do it because the kernel is easy to compute, okay? If I went to the Z space, you would have never heard from me again, okay? So this is a good way of doing it. Okay, so you look at it and it's really very pretty, okay? So first, okay, so you don't get the green thing exactly, but you can see why support vectors are called support vectors. They're just sort of holding the guy, okay? Okay, you can see it up and down, up and down, up and down. Okay, that's pretty good, okay? The other thing is that when you think of the notion of a distance, remember that that's, okay, so this is linearly separable in that space, okay? Had better be, go to the infinite dimensional space. If you don't get linear separability there, you are really in trouble, okay? And when I get the linear separability there, I get a margin. I try to maximize the margin that has already been maximized by the machinery. So I get a respectable margin. And the evidence for the respectable margin is that I do get the small number of support vectors, which are here, fine. Okay. And now when I look at the distance, the value of the margin is in the Z space. I cannot see that. Okay. But here you can see that if you look by the distance, these two support vectors are awfully close to the surface. This support vector is not that close. Well, maybe it will become close when this goes extend, but it's definitely further away in the X space as we see it, okay? But again, this is not the margin, okay? These guys are pre-images of support vectors. They are not support vectors per se, and the distance that was solved for happened in the Z space. Whatever happens here, happens here. You may end up with something that where you get support vectors far away, and here it's like a strange thing. Don't sweat bullets over it, okay? It's happening in a space that we don't understand. As long as the machinery for the solution is correct, and I get the support vectors that happen to have lambda greater than 0, I am in business. Okay, so let's shrink this back. Okay, so we get this solution, and it's a pretty nice tool to have. And we ask ourselves, was this an overkill to go to an infinite dimensional space? Yes, early on, before we studied this thing, we would say that's a complete overkill. If even for this 2 dimensions, slightly, okay? If you went to a 5th order polynomial, I would already be worried that you are really doing more much. Now you went to an infinite one, okay? But now we're asking a different question. We are asking, check the number of support vectors. That is your guide. And that is an in-sample quantity that you can observe. And that will tell you the generalization property, okay? Okay. So now we are completely sold on the idea of the kernels, okay? So now let's look at, if I give you a kernel, and it's a valid kernel that corresponds to an inner product in some Z space, how do you formulate the problem, okay? This is just formality. You already know, but just let's take it step by step. What do? You remember quadratic programming? Yes, I do. And in quadratic programming, we have this huge matrix. That is the big Q matrix that you pass on to the algorithm. And you compute it in terms of inner products. And these were genuine inner products when you were working with a linearly separable data in the X space, okay? So now the only thing you are going to do is that you, instead of passing this to the quadratic programming, you are going to pass this instead. That's it. This may not be too much computation at all. I mean, I can get the exponential and get this number, okay? And now quadratic programming is ready to go. Absolutely nothing else. If you look at the rest of the details, nothing is affected by that transformation other than this quadratic programming matrix. Okay? Okay, that's good. Now, quadratic programming passes you the alphas. You need the hypothesis. So how do I construct the hypothesis in terms of the kernel? Okay. Okay, so this is g of x equal that. I'm writing it because it's safe to write. There is a z space. I know I'm linear there, and this is the form that I have already been solving in. Now I just want to translate it in terms of the kernel. Okay? I know that I can because we spent a lot of time realizing that we don't need anything from the z space other than the inner product, and the inner product is the kernel. I just want to put the explicit form here. Okay. So you want to put this in terms of kernel of something and something. And you take W to be this, okay? And you're not going to solve for any of those. These are just for illustration. And then you get G of X would be this fellow. So you took this, substituted there. You took the inner product. The inner product, it was kernel is. You put the kernel in place of it, and you get that, okay? Now, this is very interesting because this is your model, so to speak. Support vector machines is a plural. Support vector machines doesn't dictate a particular model. You choose a kernel, and it will give you a different model. So if you have ever been curious in the middle of this, all of this jungle, what is the model? What is the hypothesis that I'm working with? It happens to have this functional form. The kernel you choose appears here. It gets summed up with coefficients. The coefficients happen to be determined by alpha. They all happen to agree in sign with the label. That's one of the artifacts of that, because alphas are non-negative. And we have plus b, okay? And again, plus b is the one that we haven't solved for, but I can solve for it using the other one, and I end up with this equation for it. Take any support vector, small m, and you can identify it by having its alpha being bigger than 0. You plug it in, and you have that, okay? So you have the full definition of your hypothesis, and you get the solution in this form, okay? And this is for any support vector, which is defined by alpha m greater than 0, okay? Now let me make a point, okay? The nonlinear transformation that started support vector machines is this guy. So in reality, I have an infinite dimensional nonlinear transformation. So each of these is a coordinate that depends fully on x. So I end up with 1, x squared, x cubed, x to the 4, if it's 1. And I could, if I'm working from an x that is more than one dimensional, I get x1, x2 squared, x1, x cubed, whole thing, okay? I just avoided the labor by using the kernel. Nonetheless, when I got the solution, I got this solution that made me completely forgot that I did a nonlinear transformation into the z-space. I can look at this and say, okay, what I'm really doing is that this is my transformation, so to speak, the case. I have however many of them as there are terms here, and each of them has a coefficient. This would be a legitimate way of looking at it, okay? The only thing to remember, and it's very important to remember, is that this transformation depends on your data set. You see this xn? Okay? This one doesn't. This one, before you gave me the data set, I decided that I'm going to use the RBF kernel, exponential. So I get 1x, x squared, x cubed, x to the 4. All of this is determined without looking at the data set. This transformation, in order to get this thing, I need to know what xn is, okay? But we have seen this before. Remember the hidden layer in neural networks? It got a nonlinear transform, okay, based on the data set. So this is not foreign to us, okay? But this tells you why this looks very simple. Where is the infinite dimensional space? I'm only determining this. This is the solution after all of the manipulation has been done. And that is why it has this form, okay? But then it will allow us to compare support vector machines to other approaches. For example, if I put the RBF kernel here, the one with e to the minus x squared, with the norm, okay? I will get a functional form. It is completely legitimate to say, okay, let me look at functional forms of that form and try to solve the learning problem based on these without ever hearing of support vectors. It's just a model. Let me see if I can get a solution. And it's very interesting to go through this exercise and to compare the result of doing it this way versus doing it the SVM route. You can also do that for neural network and other kernels that you have. Okay. Now, the question is, I am completely ready here. If you give me the kernel, everything is understood. I can solve it, and I can interpret the solution, and I can judge the quality of the solution and all of that. The only problem I have is that we don't know that the kernel is valid. If I provide, I tell you, okay, k of x and x dash is, and just give you a formula, okay? So the whole idea of the kernel is that you don't visit the Z space. So how are you going to verify that this is a valid kernel, namely an inner product in some space, without visiting that space? That's the question, okay? How do I know that Z exists? Okay, for a given kernel. So by the way, in support vector machines, you will come up with your own kernels. That will have. So it's a good idea to just ask yourself, what are what are conditions to get the kernel right? So in order to get to be the valid kernel, there are 3 approaches, okay? First approach we have already seen. This is by construction, conceptual construction, if not explicit construction. Like we did with the polynomial, we looked at it and we realized that, okay, there is a polynomial thing, and although I didn't do it for the case of q equals 100, I realized that there will be corresponding terms and I will be able to separate them. So in my mind, that is the Z space, and without constructing it explicitly, I realized that the kernel that I wrote will correspond to an inner product in that space, okay? That is a very effective approach, and the polynomial transformations are the most famous ones there, okay? The other one is the one we are going to talk about in the next slide, which is using math properties of the kernel, okay? Something called Mercer's condition, okay? So I'll talk about it, okay? I wish it was a practical condition, okay? It's a very appealing condition theoretically. You will find it a little bit difficult to apply in given situations. The good news is that people have applied it to a bunch of kernels and have declared them legitimate, so you can pick from that catalog without worrying about it, that these have already been established. It comes into play when you want to test a new kernel, not an easy endeavor, not an impossible endeavor, but not an easy endeavor, okay? The third approach is the one I find rather interesting, okay? So how do you know that Z exists? Who cares? That's approach. This is approach followed by people. Say, okay, this looks like a great machinery you have. You give me the kernel, I do this, I do that, okay? So I'll just improvise the kernel, and who cares if there is a Z space or not? I never visit it anyway, okay? So I say, wait a minute, you don't visit it, but it has to exist for all the guarantees that I talked about. Quadratic programming, and you get support vectors, and alpha greater than 0, and the generalization. All of that depends on the fact that Z space is there, and you are actually separating the data there. Believe it or not, there's quite a number of people who just improvise a kernel, apply the machinery, and see what happens, okay? And sometimes they succeed, okay? I have my reservations, let me put it this way, okay? So let's go for the mathematical route. If you actually care, okay, rather than who cares, okay? So if you design your own kernel and you want to see what happens, okay, so here is the condition. The following statement holds: the kernel that you wrote down is a valid kernel, that is, the Z space that you're talking about actually exists, if and only if, okay? 2 conditions in conjunction are satisfied. One is the fact that the kernel is symmetric. That should be abundantly obvious. Symmetric being k of x and x dash being equal to k of x dash and x. Well, this is supposed to be the dot product in the Z space, right? So you're going to transform x and x dash into z and z dash. Well, in the Z space, certainly z dot z dash is the same as z dash dot z, okay? Inner product is commutative, okay? So if this has a chance, it had better be symmetric. So this is definitely one of the conditions. The other one is that there is a matrix that we are going to require a property on. And that matrix looks like this. Similar to the one you are passing to the quadratic programming, but without the y's, okay? So what you do, you just list the value of your kernels on all the pairs coming from your data set, okay? So if this was a genuine inner product and you had it explicitly, each of these will be the inner product, this one between Z1 transpose Z1. This would be Z2 transpose Z2, etc. And therefore, this thing could be decomposed as an outer product between Z's standing and Z's sitting, okay? And you will get that, okay? So the condition here on that matrix, without visiting the Z, is that when you put these numbers, to your pleasant surprise, this needs to be positive semi-definite. That is, in matrix lingo, this matrix should be greater than or equal to 0. That's what positive semi-definite really means, conceptually. Okay? Okay, so, and this should be true for any choice of the points. And that is Mercer's condition. Now, you can see the difficulty. If I want to satisfy that this is true for any, I choose the points. So obviously, I have to have some math helping me to corner that this has to be positive semi-definite for some reason, okay? But this is indeed the condition. And if you look at the case where you know the transformation into the Z, and you put this as an outer product between a bunch of Z's and a bunch of Z's, what you are going to get is patently positive semi-definite. Because what is positive semi-definite? You put a sleeping vector here and the same vector standing here, and you are guaranteed to get a number greater than or equal to 0 for any vector. That's what positive semi-definite means, okay? If you put that and the matrix happens to be the outer product of these guys, then the guy sleeping here gets multiplied by Z, and the other guy is a transpose of that. So you get a number squared, and a number squared is always greater than or equal to 0. So the sort of the necessity part is obvious, okay? Sufficiency is a very elaborate thing to prove, and actually it is proved in a fairly elaborate integral form, not in a particular realization. But that is indeed the condition, and if you manage to establish this for any kernel, then you establish that the Z space exists, even if you don't know what the Z space is, okay? Done with kernels, that's half the deal. And now we are going to the case where the data is not linearly separable, and we still insist on separating them with making some errors, okay? And this brings us back to the old dichotomy between two types of non-separable. We have seen this before, and this actually turns out to be the subject of this lecture, if you will. So there are, if the data is non-separable, that could be slightly non-separable, like this, where these guys are just, you can take them as here and here. These are okay, as outliers, okay? I really don't want to go to a high dimensional nonlinear space in order to just go for this guy and go for this guy. It doesn't look like a plausible thing to do. And even with counting support vectors, by the time I do this and come back, I will have touched on so many points that the chances are the number of support vectors will be huge, okay? So in this case, if there is a method like the pocket where I will just make errors on those, accept an E in which is non-zero, but since the generalization is good, E out will be okay, rather than insist on E in being 0 and then go for the generalization error being huge because I use something inordinately complex, okay? So this is the slightly case. And then there is a seriously non-separable case, as in you get this, okay? It's not a question of outliers, just the surface is there, and you have to go to a nonlinear transformation. Kernels deal with this, okay? Soft margin support vector machines deal with this, okay? And in all reality, when you deal with a practical data set, the chances are the data set will have aspects of both. It will have a built-in nonlinearity, and still, even modulo that nonlinearity, some annoying guys are there just to test your learning ability, okay? And therefore, you will be combining the kernel with the soft margin support vector machines in almost all the problems that you encounter, okay? So now let's focus on this. I'm now back to the X space, okay? The data is not linearly separable, and I want to apply the support vector machine algorithm, notwithstanding that. And after I do that, I'm not going to even go back through the router. And by the way, you can transform X into Z. And by the way, you can, instead of going to Z, you do that yourself. I'll just do the basic case, and you know how to extrapolate to both the Z and to the kernel case. Okay. So here is the idea of an error measure, as we have before. I'm going to consider the margin violation. So let me have a picture and talk about it. Okay. So when you solve support vector machines in a linearly separable case, you maximize the margin, and these will be the ones that achieve the margin. And these guys will be interior points. And now we are going to consider errors. There are many ways of considering errors. I can consider the number of points I misclassify, okay? We realize that it's not a good idea to deal with the number of points that are misclassified because optimization becomes completely intractable in this case. It's a combinatorial optimization, and we discussed that when we talked about perceptron and pocket, and we said that the problem of optimizing, getting the absolute optimal in this case is generally NP hard, okay? So we are going to have a numerical value. And because the margin means something to me now, it's not a question of being on the right side of the line, it's a question of how far you are from the line. That turned out to be an important notion in support vector machines. I'm going to define my error measure based on violating the margin. Okay, so let's see what I mean. This point that used to be here has violated the margin, okay? Now, I'm not saying that once you put this here, the same solution will hold or whatever. I'm just illustrating to you what is a violation of the margin and how do I quantify it. So this is just an illustration. So this point went in, okay, in spite of the fact that it's correctly classified. Yes, because this is the line, and it's on the blue side of the line, so to speak. So there is no change in terms of the label. If I'm working with in-sample error, nothing has changed. But now I am not achieving the margin that I want for this point, and the amount of violation will be decided by this displacement. Okay? So here is what I'm going to do. This would be the case if the margin is satisfied for every point. That is the canonical form we put. And when this fails, the margin is violated. And I'd like to quantify that. So the way I'm going to quantify it, I'm going to introduce a slack for every point, potentially every point. Hopefully, most of them will satisfy the margin. Only a few of them will violate it. And I'm going to say that the quantity that used to be greater than or equal to 1 is actually greater than or equal to 1 minus a slack. Okay? So this is what allows. So the movement from here to here resulted in the red psi. Okay? And the slack is greater than or equal to 0. So I'm only considering violations. Okay? Now I'm going to consider, okay, so this is the condition, and now I'm going to penalize you for the total violation you made. What is the total violation? I'm just going to add up these violations. Okay? We have seen error measures before. We know that it's largely hand waving because I have something in mind. Either I'm thinking of an optimizer and I want to hand something friendly to it, or I'm thinking of something that is analytically plausible. Okay? This is no different. Why did I choose this instead of square? Why did I choose this instead of that? All of these are considerations that will come up when you see the result of choosing this. This is reasonable. This does seem like violating the margin. This does seem like measuring the violation of the margin. So in the absence of further evidence, one way or the other, this is a good error measure to have. And then when I plug this error measure in what we had, things will collapse completely back to where we solved it already. So this is the big advantage here. Okay? So that is going to be my error measure. So now the new optimization I'm going to do is the following. It used to be that I'm minimizing this because minimizing this maximized the margin. That was what we did the last lecture. Okay? And now I'm going to add an error term that corresponds to the violation of the margin. And it's going to be this. So this is the quantity that I promised you capture the violation of the margin. And this is a constant that gives me the relative importance of this term versus this term. This is no different from our notion of augmented error. Okay? Augmented error, we used to have the in-sample performance, which I guess would be the violation of the margin here. If you are violating too much, you'll start making errors. Plus lambda times a regularization term. This looks pretty much like a regularization term, like weight decay. Okay? So this C is actually 1 over the other lambda. Okay? But this is a standard formulation in SVM for a good reason. C will appear in a very nice way in the solution. Okay? So this is an augmented error that gives different weight. If I have C close to infinity, then what am I saying? You'd better not violate the margins. Because the slightest violation, you mess up what you are minimizing. So the end result is that you are going to pick size all of them close to 0, and then that had better be linearly separable, and that's what you are solving for. So you go back to the hard margin. If C is very, very small, then you could be violating the margin right and left. Okay? So nominally, you are getting a great margin. Okay? But you are violating it very frequently. Okay? And there is a compromise here. Okay? But that's what you are minimizing. Subject to, this is what I had before. Okay? And now the condition adds psi to it. So I'm requiring this to be the case. And I said that psi's are non-negative. I'm only penalizing the violating of the margin. I'm not rewarding the anti-violation of the margin. If there is, here's the thing, and one of the points is there, good for it. Okay? I'm not going to give it credit that allows me to violate the other guys, because that is not going to help me. Okay? So psi is non-negative, and I get this condition for all points, all capital N of them. Okay? And finally, I have the range in which I'm optimizing, which used to be this, and now I have the size being R to the N, I guess the positive, but that is captured by the constraint. If you look at this slide, okay, take out the red, and you have the problem you already solved. The hard margin SVM is in the linearly separable case. So this is the added guy. So now what we are going to do, we are actually going to go through the Lagrangian again, okay, because the Lagrangian is not that much different from before, so you can take it as a review. And the good thing is that if you thought that the terms dropped right and left before, wait until you see this one. Okay, so here's the Lagrange formulation. We have L of W, B, and alpha, and some missing guys that will be filled. And we have this and minus that. So you can see that it's spread out because obviously I'm going to put the new stuff in. What I put here is exactly the Lagrangian you worked with before. This was your target. This was the zero form of the inequality. That is, mean this minus 1 is greater than or equal to 0. You put that in multiplied by the Lagrange multiplier, which is non-negative, minus because it's in the form of greater than or equal to. And this is your Lagrangian that we solved, and we ended up with the quadratic programming problem we had. So now there is a new guy, which is psi. That's a new variable that I am determining. Okay? How does it appear in the Lagrangian? Well, the target is no longer just minimizing this, but minimizing this plus the other guy that penalizes the violation of the margin. So let's put that. Right? Okay. Now, the constraint that I had used to be this is greater than or equal to 1, so I had it as minus 1 for the 0 form. Okay? The new constraint is this is greater than or equal to 1 minus psi. Right? So I need to put the new constraint, and when you put it minus minus, you get the plus. So that's the word, okay? Now, the other guy is that I have a bunch of constraints on psi itself. I need to put them in the Lagrangian form. And this would be this. Okay, not scary at all. Psi n is really the constraint on psi in the 0 form. A little bit rabbit. Psi is greater than or equal to 0. So if I wanted to put it in the 0 form, then I put psi. That has to be greater than or equal to 0. Pretty much like this fellow had to be greater than or equal to 0. I need to multiply it by a Lagrange multiplier, a new guy. So I call this guys beta. Okay? And I do this for all the constraints, capital N of them, and I have a minus because this is in the direction greater than or equal to. So absolutely nothing different here. Okay? And now I add the new Lagrange multipliers to my, and I get this fellow. Okay? Now I'm proud of this because of a reason. Okay? The slides are widescreen for this course, right? Okay? Okay? I had to have an equation that takes the full width of the, okay? And finally, in lecture number 15, I managed to do that, okay? Now, you say, forget it. This is just too complicated. Please bear with me, because terms will be dropping like flies, okay? So just follow this and see where we arrive. Okay. So we are going to maximize this with respect to W and B, which we used to do, and with respect to psi, which is our new guys. Minimize. And then we are going to maximize with respect to the Lagrange multipliers, the alphas, which we used to have, and the betas are the new guys in town. Okay? So let's do the first guy. Let's do the minimization with respect to W, which we did before. Okay? Can you differentiate this with respect to W? Okay? I will get a W here. This red guy doesn't contribute. Here I will get what I used to get. This guy doesn't interfere. This guy doesn't play a role. That's encouraging. I am actually getting what I got before. Okay? Let's do partial by partial B. Okay? Does this guy play any role? Does this guy play any role? This guy gets multiplied by here. Does this guy, B doesn't appear here. I get exactly what I got before. Okay? So the final guy is to get the partial by partial size. That's the new guy. So you do this. Let's see what happens. I'll do it one at a time. So there are capital N of those. I didn't put it as a gradient just to make it simple. So I put it at one at a time. And I see, okay, psi n gets multiplied by C. Psi n gets multiplied by alpha with a negative sign. Psi gets multiplied by a beta with a negative sign. So if I differentiate with respect to psi, this is what I'm going to get. C minus alpha minus beta, equate that with 0. Okay? Now, isn't that grand? Because now you are saying that this quantity is always 0 for any small n from 1 to capital N. Okay? Let's look at the ramifications as far as the Lagrangian when you substitute in the Lagrangian. Here I have a C. Here I have a minus alpha. Here I have a minus beta. These are multiplied by psi. Well, that combination happens to be 0. So conveniently, this guy and this guy and this guy together with his beta are dropping out. we are back to exactly the same Lagrangian we had before with exactly the same solution we had before, okay? And what happened to beta? Well, beta did its service, and we thank it for its great service, and we bid farewell, okay? It's gone, okay? The only ramification of beta that we have is that because beta is greater than or equal to 0, and we have this condition, alpha is not only greater than or equal to 0, which is what it used to be, it also cannot be bigger than c. Because if it's bigger than c, this quantity becomes negative. And all of a sudden, I cannot find a legitimate beta to make this true. So the only thing out of all of this adventure is that we are going to require that alpha be at most c. So everything before plus this added condition. That's the whole thing, okay? So you get the solution. You get this. That's what we saw before with respect to alpha, and beta doesn't appear. And you have alphas being non-negative with the added red condition. That's the only thing which is added, less than or equal to c. The inequality constraint is there, the equality constraint that is inherited from the condition from the previous slide, same as we did before, okay? And when you get the solution, W will be this, okay? And W will guarantee that you are minimizing this plus the new objective, okay? So if you have already wrote your routine in order to apply support vector machines, all you need to do now is go to that routine, and instead of 0 less than or equal to alpha less than or equal to infinity, make it 0 less than or equal to alpha less than or equal to c. And you have the soft margin support vector machines. Okay, that is good bargain. So let's look at just very quickly types of support vectors. Okay, so this is a picture. And this is the pictures where you have support vectors in the hard margin case. There are only two types of points here. Interior, where the margin is greater than 1 strictly, and boundary guys that happen to be support vectors with the margin is exactly 1, or at least the quantity that corresponds to the margin is exactly 1, okay? And that is all I have. Now, when you have the soft version, we are going to label these guys margin support vectors, just because there will be other guys that violate the margin, okay? And they will be support vectors. They will get Lagrange multipliers that are greater than 1, okay? And in this case, the margin support vectors that used to be just alpha greater than 0, they also happen to be strictly less than c, okay? You can look at it independently because in order to understand, but let me just give you the hint here, okay? When alpha hits c, beta, the lost multiplier, hits 0. We know when the Lagrange multiplier hits 0, the corresponding slack has to become positive. That was one of the conditions we had, okay? And therefore, because here the slack is 0, you actually don't have psi is 0, you have be clear of c. That's the reason for it, okay? So this is the condition for those guys, and psi is 0, and these are the guys you use to solve in order to get the b, and so these are as clean as they used to be. Now we add the non-margin support vectors, okay? And by those, we mean that now alpha n equals c. So it's positive. They are support vectors. Alpha n is greater than 0. But they happen to hit c. And now I have a slack. The slack psi starts becoming positive, okay? And therefore, the margin is violated. I am less than 1, okay? So that's 1 minus psi, and psi is positive. Indeed, psi is positive in this case, okay? So let's look at those non-margin support vectors and see what they look like, okay? So again, just for illustration, I'm going to take these 2 points and start making them violate the margin. Not that the new solution will be exactly the same, except that these guys are inside. You have to resolve it with C, etc. But I'm just illustrating just to show you the point, okay? So this is one way to violate the margin. You violated the margin, but you are still classifying them correctly. These are non-margin support vectors, one type. You can violate it further and cross. So now these points are misclassified, okay? And they are still non-margin support vectors, and now the En is affected. And you can go wild, and you are just completely deep, okay? Okay. So all of as long as you are violating, you are a support vector, okay? Not a clean support vector, but a support vector nonetheless, okay? Now, the value of C, okay, is a very important parameter here because it tells us how much violation we have versus the width of the yellow region. And this is a quantity that will be decided in a practical problem using old-fashioned cross-validation, okay? This is a point, a parameter that we need to determine, and whenever we have one parameter to determine and we want to pick it optimally, we can use cross-validation. So as you see, validation and cross-validation are a layer on top of this. Here I am using a very elaborate algorithm which supports vector machines, yet I am resorting to cross-validation in order to determine C. Okay, I'll make 2 quick technical remarks and end the lecture here, okay? These are just practical points in case they bother you. If you didn't see them, they are not going to bother you. So here is the idea. With the hard margin, I apply this machinery, I get the dual, pass it to quadratic programming. So I'm asking myself, if the data is not linearly separable, what gives? Because think about it. I never told you to check that the data is linearly separable. I gave you the data, minimize this subject to that. Now, if the data is not linearly separable, subject to that will be impossible to satisfy. There will be no feasible solution, okay? Nonetheless, this didn't prevent me from getting a dual and passing it to quadratic programming, okay? And maybe quadratic programming will give me back a solution. So now I'm in a strange world, okay? So the key thing to realize is that the translation from the primal form, minimizing W transpose W, to the dual form, maximizing with respect to alpha the Lagrangian, that step is mathematically valid only if there is a feasible solution. The KKT conditions are necessary, so they have to be satisfied if the point is there, okay? Obviously, if there is no point in the domain, then I'm now working pretty much like the guy who improvised the kernel that does not correspond to a Z-space. Yeah, you can plug it in and get a solution, and no guarantees there, okay? In this case, actually, if you go to the Lagrangian, the quadratic programming will try to converge to something in infinity. But you need not to worry about this case at all. Let's say that you have a buggy quadratic programming, and you innocently translate the problem into the dual. You pass on to quadratic programming. Quadratic programming passes alphas back to you, okay? Now, it's impossible that all of a sudden the data became linearly separable, right? You don't have to worry. You can always check if the solution separates the data. You can evaluate the solution on every point, compare it with the label, okay? And when you realize that it's not agreeing with the label, you realize that something is wrong, okay? So you don't have to go through the combinatorial problem. Is this linearly separable in the first place? Should I run the perceptron first to see if it converges before? No. Just be lazy if you want and go through this. And when it comes back, check. If it's linearly separable, things are valid. There is a feasible solution. The dual solution is valid and quadratic programming works. If it's not, then something went wrong. Chances are you won't get to that stage because quadratic programming will be complaining. But quadratic programming will be complaining anyway, as you may have experienced when you try it, okay? Tells you ill conditioned, and sometimes you have tweaks. Let me put a bound on this in order not to make it go into a bad region and whatnot. So it's not a perfect package, okay? So this is just a reminder that we will never be susceptible to a big mistake like getting a solution when none exists. The last point is when we transform to the Z-space, you may have noticed that some of the transformation had a constant coordinate, 1, right? 1 in our mind used to correspond to W0. We made it a point at the beginning of discussing support vectors that there is no W0. We took it out and called it B, the bias. We treated it differently, okay? So now we are working with both W0 and B, because if you have a constant, okay, I mean, you may not call it W0, but effectively it's W0. It's the guy that gets multiplied by the constant. So what gives? Now I have 2 guys that play the same role. And you don't have to worry about that. Have the Z-space have 20 constant coordinates. Don't worry about it. Because of what? Because when you get the solution, all of the corresponding weights will go to 0, and all the bulk of the bias will go to the B, okay? How do I know that? Because you are charged for the size of W, because it's part of W. You are minimizing half W transpose W, okay? You are not charged for the size of B. So obviously, if you want to minimize and you can do it with both, everything will go to the B and this guy will go to 0. So we need to worry about that. Okay, with that, we will stop here and we'll take questions after a short break. Okay, so let's start the Q&A, and we have an in-house question.
Hi. It seems intuitive to me that the number of support vectors goes linearly with the dimension of the space that you're looking at.
Okay.
For example, in an n-dimensional Euclidean space, you need n vectors to define a n-1 dimensional hyperplane and one other to define the thickness of the fat plane, right?
Okay. It's not that easy because you could get. I mean, I could get two clusters that are far away of points. Okay. And then 2 points that are +1 and -1 that are close to each other, okay? And in order to separate, I have to be sandwiched here, and then I am guided by okay, these guys may have, you know, I have the orientation here, and the orientation is decided by the 2 points that are around me. So, in spite of the fact that in a general case I will do that, I could construct cases where it's not linear in the dimension. Let's put it this way.
So you're saying it's less than linear. It's better than linear.
It's better.
Usually better.
Yeah. And obviously, if it was completely linear and I transform it to the infinite dimensional space, I obviously would be in trouble.
Yes, that's my.
So that was the question. Yes. Yeah.
But it should go positively with the dimension.
It's likely to increase with the increasing dimension. Okay. And the exact form depends on the data set and depends on the position of the data set, including the interior points. I could have I mean, let me put it this way. If I give you, even without considering the interior points, let's say I give you 2 points, 1 + 1 and 1 - 1, okay? There is an optimal separating plane. And how many support vectors am I going to get? I cannot get more than 2 because I only have 2, even if I go to 100-dimensional space. So so the linearity is an impression that requires further assumptions, but in general, it will not hold.
Yes, and for example, the RBF kernel, it may, in its form, it looks like infinite dimensional, but in reality, I think its effective dimension is very small because the higher order terms decay very fast. Right?
And
decay with both an exponential term and a factorial term.
Completely agree, and indeed that affects it because you are actually measuring a distance proper, a Euclidean distance proper in that space. So if a dimension is very small, then it doesn't, affect it very much. Okay, so I mean, it's whether it's a really infinite dimensional or infinite dimensional in disguise. Generally, when you have an infinite dimensional space, the only way to really define an inner product is to have a decaying term so that the thing converges. Okay, so this is essential when you want to compute.
So if it doesn't converge, say you change the negative sign in the RBF kernel into positive signs,
okay,
then it won't be.
But I mean, the inner product now is not well defined, right?
So it won't be a valid kernel, and you'll get horrible.
Yeah. I mean, because a valid kernel, I have to be able to evaluate the inner product, and infinity would not. I mean, or lack of convergence would not allow that, right?
Yeah. Okay. Thanks.
Absolutely.
Okay, so people are curious, how can you generalize SVMs to a regression case? So for
there is a huge body of knowledge for generalizing it, and I didn't touch on it for 2 reasons. Again, pretty much like when I did the VC analysis, it's more technical, and I get the basic concept without having to go through the technicality. The other aspect is that the major success of support vector machines is really in classification. Okay. They are not as successful competitively in regression. That's the practical experience. So I have found that it's not worth the amount of time to go into that.
So is it safe to assume then that in the infinite that if you do the transformation to an infinite dimensional space, the data will be linearly separable there?
It is safe but not certain. Okay, I can create situations that are opposed to that. But again, this is one of the reasons why I made the final remarks there, because let's say that I took my data and applied RBF. I really don't know whether they would be linearly separable in that space or not. I just applied the machinery, but I can always find what the solution back and see if the points are classified correctly. Yeah.
Also a technical question on the quadratic programming. So usually if the matrix you give is not positive definite, there will be complaints or there will not be complaints. That's people
okay, my experience with quadratic programming, there are tons of packages there, so I'm describing a subset of them necessarily, the ones I tried. Okay, they tend to complain. Okay, And it's it's almost like, you know, when you use MATLAB and it tells you the condition, please get me the inverse, and it tells you the condition number is bad, and so on. Okay, so in most of the cases, even with the complaint, the solution is fine. Okay, it just has a you know, a certain reliability that it has to have in order not to complain. So invariably, when you use quadratic programming, there will be a complaint one way or the other. Okay, but I have learned not to be completely discouraged by that and tweak limit variables and whatnot. But this is just completely a practical situation depending on the package.
Well, going back to the previous question, so when you said safe but not certain, so does that mean just in very degenerate cases, or but in
okay,
or
with a real data set that is not completely ridiculous? Okay, I have never seen it happen. Okay, you can always do. I mean, you can have. I mean, in some sense, you can have especially with the radial basis function, you can have one on top of each point and whatnot, so you can separate whatever is there. Okay, so I have not encountered it.
So another question is it possible to combine kernels to produce like new different kernels? How useful is it to, you know?
Okay, you can do it as long as the combination is legitimate, that it maintains that there is a Z space in which this is an inner product. That's really the requirement. Okay, if you have that, then I mean, okay, there are many variations of the methods, the basic SVM method that are in the literature. People tried several things. And you know, as long as what you are doing is legitimate, so that you have the generalization guarantees of SVM, it can be done.
Since we are only talking about inner products and they usually induce a norm, are we always preferring the Euclidean norm, or can it still be changed and still use inner products?
The way I derived it based on Euclidean norm and straightforward inner product. Okay. There are obviously variations of that you can get and still have the machinery go through with modified quantities. Okay, so it's not impossible, but you just need to make sure that the quadratic programming problem you are solving corresponds to the version of the norms that you used and the version of the inner product that you used.
What would you say is the scale of the problems that can be solved by SVMs, again, the number of points? Or
the scale of problems that can be solved by quadratic programming is a more pointed question, because that's the bottleneck. Okay, okay. So okay. I mean, it depends on. I mean, if you are using MATLAB versus something else, they get saturated at different stages. Okay, I would say if you get to 10,000 points, that's pretty formidable. Okay, and if you are below 1,000, you should be okay, but some packages will still give you a hard time. There are packages specifically for SVM that use heuristics, so they don't specifically pass on the thing to quadratic programming directly, but try to break it into pieces, get support vectors for each case, and then get the union and so on, the hierarchical methods and other methods. So they are basically heuristic methods for solving SVM when straightforward quadratic programming will fail. And these are also available and should be used when you have too many data points.
I think that's
okay,
it.
very good. Okay, so we'll see you on Thursday.